Okay, I think we're ready to get started here. So it is now after Easter. We had a really late Easter break. Hopefully you had a little bit of a break. You know, some of you probably did not have much of a break. Uh, I got to go to Seattle. My wife and I flew to Seattle to visit our son, so we got to get away for a little bit. So that was nice. So we're on week 14. So we only have basically 2 weeks left. And so we'll continue to cover some topics. Today we're going to cover self-driving cars, which is chapter 16 in our textbook, and look at those. We'll do that today. And then tomorrow for our lab, we won't really have a lab. We'll just have a final project work day. The goal will be to work on the final project a lot, get a kind of hopefully a minimal viable project working, something done. I know some of you, like a lot of these projects, you might have to update or write an image to an SD card. If you haven't done that, we'll have computers here and we can overwrite an SD card with the new image for, like, if you're doing RetroPie or something like that. We'll talk about that. I'll have some of the hardware there, so if you need a camera or something like that, we can try to get that configured, that sort of stuff. So Thursday, we'll spend the whole day just trying to make some progress on your final project, actually working with your Pies, trying to get them with the right software and right stuff, so that hopefully by the end of the week you have some somewhat working solution. I always think, to me, a minimal viable product is something that's doing like 40% of what your final project should do. So just showing that you can do something there for that. So that'll be our goal this week on Thursday. But today we're just going to do we're going to learn about self-driving cars and the architecture for self-driving cars for this. So I'm going to go over it now. I'd suggest you go to Unit 14. Yeah, I think initially I did Unit 14 invisible, but it should be visible now. And you should go to the exercise and open that up and start working on that as I talk about the self-driving cars today for this. So let's talk. I'll just warn you, self-driving cars is something I'm very excited about. I wish we had more self-driving cars now, but that and robotics are one area I do stuff. In the last class I was in, we just did a whole section on robotics. So it's kind of fun now to turn to self-driving cars. So has anyone been, so what's the most self-driving car you've been in? So for example, I was just, we're in Seattle, we rented a car. It was a Toyota Camry, I think it was there, but it had lane assist and adaptive cruise control, which I'm used to. So again, you get on the highway, you set the cruise control, and it'll go at that speed. It slows down when you get to another car and follows at the speed of whatever car is in front of you. If you veer off of the lane, it will it'll pull your wheel back to keep you in your lane there. So that is, I think, pretty common on new cars in the United States, is that lane correction and adaptive cruise control. Has anyone been in a car that's been more self-driving than that?
Yeah, I've been in a Waymo. So like in San Francisco, they have like Waymos. So it's basically like put into your phone, and it comes to the position that you are, and then you have to open it with the phone, and like just basically tries to solve around the whole city. And, like,
and there's not a driver in there at all?
There's literally no driver, it just like drives itself.
Right. Okay, and so you're in San Francisco and you did Waymo. So Waymo is, that's kind of like Uber with self-driving cars, right? I mean, you know, that you order it on your phone, it drives up to you, you get into it, you tell it where to go and drops you off. How did it do?
It does really well, because like it has like a big camera that literally analyzes everything, like it makes decisions, it's like literally, it's just literally another person in the car, literally, because it's like it has this, I don't know, this camera that analyzes everything using infrared, so you can identify like blocks in front of it, you can identify a person, you
Right,
can literally like divert out the road if a person is in
Right.
front, or you can
Yeah.
stop, like it's literally precise.
yeah, cool. Anyone else been in a self-driving car? Okay, so let's talk about how these cars work and some of the architecture for that stuff. So again, normal stuff, we've got to worry about gear selection if it's you know, going park, forward versus what I was in a rental car. Oh, I think I was in the college vehicle the other day, and I hadn't been in the college vehicle, that van. I could not figure out how to put it in reverse. I couldn't even figure out where the gear, you know, well, you know, I'm used to some big handle to do it, and it was some little thing there. It took me 5 minutes to figure out how to. So gear selection, of course, steering there, acceleration and braking. And again, these used to not be built into cars, but nowadays most cars have some of this built in automatically now, again, for lane correction, for cruise control, and that sort of stuff here. So let's talk about autonomous driving levels here. I wonder if this website is still active. Yes. So this is an organization that was trying to, you know, has been trying to like define the different levels of autonomy in these self-driving cars here. And level 0 is just no driving autonomy, so basically a dumb car. Level 1 is driver assistance here. So you can perform either steering control, acceleration, deceleration control for sustained periods, but not both, maybe simultaneously. So again, they're talking about lane keeping is one, or adaptive cruise control is the other one. Now I'm actually seeing them both together here, but that type of basic ability is level 1. Level 2 is partial driving automation. So again, maybe doing both. And again, I'm seeing cars that do both now, like our rental car did both. I would say it was level 2. It could keep you in the lane and adaptive cruise. So technically, when I was on the interstate, I could have probably just let go of the wheel and it would keep me in the lane and it wouldn't hit the car in front of me and it would just go in a set cruise there. So I have a 2018 Subaru right now, and I can do that. I can let go of the wheel, but it complains. It is not a happy car. It just flashes like this. Remember, put your hands on the steering wheel. Remember, put your hands on the steering wheel when I do that. So it is not made to do that, but it can do that. Again, with adaptive cruise control and self-drive and staying in the lane, it's just not happy about it. Level 2 would be, I think, a little happier about it. So, level 3 is driving automation, where you can do it for sustained periods of time here. And so often what I think of this is, you know, you might have to get out of your driveway or in a parking lot. And that's what I always wonder about Waymos. How good are they at, you know, parking lots and stuff like that? And or things like that. But when you get onto the streets or, you know, on the main thoroughfare or whatever, standard roads, then you can switch to autonomous mode and it will drive you there for that. Now, one thing I want you to do is to find cars at each of these levels here. So for your exercise, you should describe, we have each of these levels So you want to list each level. So again, give a short sentence about what each level is, and then an example car in this area for this. You can try to use AI for this. Watch AI tends to sometimes make things up, so you might want to verify, but AI will certainly be able to describe these 5 levels here. You might have to refer, so this is, what is this from? You might want to refer to the Society of Automotive Engineers here, 6 levels of driving there. So if you ask AI to refer to the Society of Automotive Engineers stuff, they can easily kind of give this same sort of 1-sentence description. But then see if you can come up with cars that are that way here. So just look, because I think oops, on custom. Yeah, I'm going to turn on search here so it can search the internet. Give me 3 different examples of cars in level 2 of levels. Let's see how it does with level 2. I think most things will be in level 2. But again, I said level 2. Okay, and it's doing more like the Tesla. I would classify that not as level 2 here because it says it is, but I mean it requires driver supervision, but it can self-drive itself here. So I would read these definitions and watch AI. If you're using AI for this, just know that AI you may have to almost provide a level 2 description and see if that will help. So, but again, come up with example cars in each area. Level 4 is high driver automation here. System can perform all driving tasks for sustained periods of time, also capable of automatically reacting to unexpected events, minimal risk, that sort of stuff. I would say like Tesla would be more like level 4 currently with the current version. I don't know. I haven't been in a Tesla, but my understanding is they can drive around pretty well once you get them going, and they can navigate parking lots and stuff like that. And then level 5, like someone was just saying, Waymo is a good example of level 5, fully autonomous stuff. So this was saying back in 2021, most vehicles on the road were level 0. I currently think in 2025, most vehicles are now at level 2 here, where we can do simultaneous steering control and acceleration, deceleration control on most cars. At least that's an option for most cars out there for this. Concerns here, worried about different things, following the road, obeying traffic signs, obstacle avoidance here. And this edge case is a big thing where you might, program it to handle lots of cases, lots of examples of things. Like in Minnesota, you can have a car trained to drive in the along the road, identify people on bikes and people walking and other cars, maybe even handle deer and squirrels and other animals there. But the edge cases, so what happens when you see a wild turkey on the in your lane and you've never seen a wild turkey or you haven't trained on? What about snowstorms? Maybe you haven't trained in a snowstorm very well. And how do you handle those cases, or even more edge cases? Um, a while back we had a flood, and I think some of the penguins got out of the zoo. So you probably haven't trained your car, and they were out in Central Avenue. So, penguins are probably not something you trained your self-driving car to avoid. So how does it handle penguins here? So, um, So we want to talk a little bit about how they're sensing their surroundings and stuff, and some of the sensors for this. So some of these you're familiar with, certainly speedometers you're used to having, right? All cars have a speedometer tied to the wheels here. GPS you're familiar with, navigating with the GPS and maps. It was really strange. Usually I find GPS pretty accurate, but when we were driving through Seattle, not just the last day, we were one like 10-mile section of highway. And again, it was raining slightly. I don't know if this was causing a problem, but our GPS was really off in the car. Because again, we are mapping, and usually it keeps you on my lane, but when we were mapping, it kept shifting us and thinking we were on the frontage road, not on the highway, and then giving us directions to try to get back on the highway, because it would think, and then it would put us on the frontage road for a couple minutes, and then it would shift us over. And sometimes when you're trying, it was just not being very accurate. So I don't know what was happening with GPS there, but GPS can have problems. Now, there are ways to make GPS much more accurate here, especially if you have fixed locations, but this doesn't really happen that well with cars. I have a friend who is an archaeologist, and he uses GPS when he's digging on nice sites, because if he puts so GPS works with satellites, right? There's satellites way up the sky. We pick out 3 satellites where they all have atomic clocks. They all send a time down to your car or your little phone or whatever. And your phone looks at all the different times, and they're subtly different, and it can triangulate where it's at based on those 3 times. But if you add a local one, and again, you can do this with the right materials, you can, and again, sometimes on highway or construction, you'll see people with there's physical location at a special site. Usually there's a brass plaque on the ground. You can put something there that sends out a GPS, and then you can get GPS measurements down to the centimeter space, which is what you need when you're like doing archaeology and stuff like that. So, let's talk a little bit about some of the other sensors. Oops, I'm having trouble with this. Let's try this again. I'm going to talk about filters and particle filters, which is an example of a Kalman filter, in just a sec for how we do location. But I'm going to talk about some of these other things too. Video cameras, like you were saying, that a lot of these cameras have cameras on them. Even my 2018 Subaru has 2 cameras built into the screens to keep track of lanes and stuff like that. So a lot of cars have cameras in it on them. Radar, again, not so popular. Again, this is what you see on satellites, but what is getting more very common is LiDAR units. Are you guys familiar with LiDAR units? You may be, and you're just not familiar with it. So this is our little robot. One of our little robots we use for doing what we'll call SLAM, doing simple robot navigation here. And this is, let me show over here. This is the LiDAR unit on top. It sends out an invisible beam here, and it spins around. So it'll spin around at about like this rate, and basically it scans line, so it'll detect all the walls. This one isn't very strong, so like if it were here, it'd be detecting these walls, and these walls. It wouldn't detect all the way to those walls, those are just too far. It range is probably 10 feet or so on this unit, there. If you, do you know what this is? Vacuum, it's our little vacuum, here, not all of them. So we have two vacuums. We have a dumb vacuum that just drives around. It has bump sensors in it. It just drives till it hits the wall, bumps into it, turns a random amount, drives somewhere else, hits the wall, turns around, drives somewhere else, and that's how it vacuums. It's funny because you can just, we have carpet in the basement. You can just see the random paths all over where it's bumped all around, driven all around the carpet there. But this vacuum is a smart vacuum. It is mapping, so it has a LiDAR unit right in here that spins around, basically something like that. It is spinning around in there, and you can see there's a little, you can see where the little light set. Again, it's not visible light, so it's sending out like a little laser, but it's not visible, doesn't hurt you or anything like that. But that's, so often you'll see those, and so this kind of stuff will map out the whole house and where things are at with the house there. And again, usually they come with an app, and you can actually then bring up, right, you can bring up the app and see it mapped out your whole house and how in the path it chose to drive around the house. So that is LiDAR here. Sonar is, again, sound instead of light for this, and that's often for short distances. So again, some of these things will have bump sensors in them, but like your car, you probably don't want your car to just bump into things and then turn around. That's not going to work. So you have, I mean, if you look at your car, you'll see these little circular sensors about this far around your car lot. So like not mine, but my wife's car drives me crazy. It's a Prius, and anytime I back out of the garage or back up anywhere, it beeps at me and flashes these lights. Oh, you're too close to the left side. You're too close, right? Do you get those things? It's constantly, because again, it has these little sonar sensors all around the car, and then as soon as I get too close to something, it beeps there. Not touching it, it just gets close. So again, that's our sonar sensor. So that's what we're using to perceive this environment. Now, how do we handle all these things? Let's talk a little bit about Kalman filters here. Let's see, how are we doing on, oops. Oh, I forgot. Okay, I jumped into the GPS. I forgot to tell you about, because someone was talking about Waymo, and this is the closest I can get to Waymo here. Is I grew up in Grand Rapids. It's a little town out of here, and they've been test driving a self-driving car, very much like Waymo. So, if you go to Grand Rapids, you'd see this car driving around, and it is a test vehicle for autonomous transit. A lot of communities like Grand Rapids have a free taxi, kind of like an Uber, for people who qualify for its use there. So people who might be at a certain income threshold or have certain needs, elderly, that sort of stuff. So you could qualify and use this free transportation. So a lot of communities have these free transportations, and sometimes they'll have a volunteer person driving a little van around. Sometimes, often there's a paid person who's driving and pick you up, and you can just call and say, I need a ride to the doctor or to get my prescription filled. And the person in the van will come pick you up and drop you off there. So that's pretty common in a lot of, at least Minnesota communities, is this. And again, it may be free for everyone, but generally not. Usually it's free for if you qualify for that. And so this was the same thing, but autonomous here. So there was an autonomous car. You can see the big LiDAR version here for this and set up for this. And there's actually, it wasn't like a Waymo in that there was always a driver in the vehicle, but the driver was not driving, it was helping. So like if you want, a lot of people, it was common for people like to need assistance with wheelchair and that sort of stuff. So the driver or the assistant would be there for that stuff. So let's see if, so again, we see this vehicle around a lot here, and it had a LiDAR on it and stuff like that. So in Grand Rapids is a town of 8,000 people. They've just been testing that. They were testing it in the city, but they also wanted to test it in a rural area. So they were testing it out in rural Grand Rapids, where I grew up, which was always kind of cool. So that's what this Go Marty is here. So, okay. So we talked about GPS here. And again, you're picking up at least three satellites. Because again, if you have three satellites, you can pick out your location. If you don't, you're going to have it. That's why, I don't know if you ever know, GPS doesn't work inside very much. So often if you're inside the building, like if I'm working out in the gym and I'm using my app to track myself running around the track inside, it's not going to track me running inside because it can't get a good GPS lock generally on me inside, things like that. It's going to have to track me some other way than GPS for this here. Again, these are other sensors. You can do a little research for some of these sensors. But let's talk about localization here and filters. Filters are not, when I always think of filters, I think of like a water filter or a coffee filter where you put stuff in, you put water and it drains and only lets certain things out. That's not exactly what this is. And there's image filters. It's just the idea of like filtering a bunch of sensor readings down to a selection, maybe. So SLAM is something called, well, two things we have to do when we're navigating around. One is we have to localize where we are here. And so localization is this process of trying to figure out where you are. Let me see if I can, we'll make this a little bigger. Let's see. So in this image, the blue dot is the robot, and we're trying to figure out where the robot is, and that's localization here. And so the red dots are all guesses where the robot might be. And eventually we get a pretty good guess of where the robot is here. And all the red dots are in the same area, and the average of the red dots is a yellow dot, and that's right where that robot actually is here. So this is what localization is just trying to figure out where you are on a map. So that's one challenge you have to do when driving around, is where are you on a map? The other thing is sometimes if you've never been to a location, you don't have a map. You might not have Google Maps. So you might have like Google Maps for some area, but Google Maps is not going to maybe be in all the parking lots in a parking garage or in, your driveway or places like that. Google Maps doesn't have all that stuff mapped. So you might have to map it out as you're driving. So as you're driving a robot around like this, it's sensing out the sensors and it's detecting where the road is, where boulders are, where trees are and stuff like that. It's creating a visual map, an internal map of it. So SLAM is simultaneous localization and mapping, where we do the same thing, where we're driving in a new area, we're mapping it out, and we're also localizing us in this area for this. Now, one of the common ways of doing this is called particle filters, which is a version of what the book calls Kalman filters here. It's possible to combine measurements from multiple sources like GPSs, internal sensors. So you create a mathematical model of this to kind of constrain where you are. So Kalman filters synthesize the available information and produce an estimate of the vehicle's state, significantly more accurate than one sensor can provide. I'm going to see if I can get, I have this code for Kalman filters written in Java here. So, see if I can run this if it was run. So here's a program that's running Kalman filters. So it has a robot here in blue, and the robot's facing a certain direction. It's got kind of a long nose pointing ahead here. So that's where the robot is. And then the computer randomly guesses where the robot is, and that's this yellow location here. And it just randomly picked a spot. The robot also, the computer is going to want to look at the sensor readings. So the robot's got to have a set of sensor readings, maybe LiDAR, maybe GPS and stuff. To have a sense of these numbers. And then based on those, it's going to try to guess where it's at. And so what we do, how filtering works, is we create a bunch of ghost robots. And that's where all the red ones are. So we create these random ghosts that are all little ghost robots that all are facing a direction. And each of them, we figure out what the sensor reading should be there, and we compare it to the actual robot readings. And again, readings are kind of noisy and they'll jump around a little bit and they're not always accurate. I was just working with someone, even working with a Raspberry Pi doing weather sensors, and he was running into this problem where he was getting the like temperature, it would read it fine for a couple, and then it would just stop, and the sensor would go bad for like half a second, and then go in and out. So like once a minute, the sensor would just flicker out and we couldn't quite figure out why. But that's pretty common with sensors, is they're not 100% accurate 100% of the time. So now, if I move, I'm going to try to step forward here. I'm going to have the robot step forward. When the robot steps forward, we're going to have all these other robots step forward too in their simulation. And I've highlighted some of them just to kind of show you what their LiDAR readings are doing. And then we have the robot's LiDAR readings and other sensor readings. And then if a LiDAR reading isn't very close to matching the robot, we're going to get rid of it and recreate it somewhere else. So as I step forward, a lot of these robot readings will not work because my robot is going to, if it looks ahead, it should see a bunch of space. It should see a wall to the right, left, and a wall to the right, and a lot of space behind it. So like some of these sensors, like even over here, it looks out through this door and it says that looks good. It can look behind it a ways, but there might be a wall to the right or left. So some of these could be where the robot is. It isn't, but it is still not sure. But as the robot moves, especially if the robot turns around in different ways, as it kind of turns around and figures out where it's at, the robot will decide where it's going to be at. So eventually, the robot, all the little ghosts will be huddled around the robot. And the robot will have a really good approximation of where it's at for this. So we move it. So Kalman filters are this way of, we create all these little ghost versions of it, and the average of all the ghosts is it. So you can actually see here, the blue is the robot, but almost exactly beneath it is the yellow square, which is where the computer thinks the robot is for this here. And all the green lines are some of the different sensor readings from the robot. And again, the code for that, this isn't a programming course, but the code for that isn't too bad. If I, let's see. If I look at the code for that, these particle filters, you know what a particle is just it keeps track of where it's at, its orientation, the distance it's sensing, its fitness, probability, so it keeps track of some information. So again, some lines of code there. And then the particle filter will select best particles and stuff like that. So there's a little code in there, but it's not that bad to do that sort of stuff. So, okay, let's go back to the textbooks. See it. Okay, we're talking about these different types of sensors. Let's talk about convolutional neural networks. I just wondering, I get to teach the machine learning class, and we spend a fair amount of time on convolutional neural networks. So I'm used to spending a couple of weeks on these, and so we're just going to spend 10 minutes on these, so it's kind of sad. But I can introduce you to these convolutional neural networks here. So again, neural networks are a machine or an AI model or machine learning model that's trying to capture images, and it's based on your brain. So I don't know if you remember your anatomy class, how your brain works, or your eyes work. Your eyes pick up vision. Rods and cones detect signals that are transmitted to the back of your brain. That's where your visual cortex is. And there are different regions, often called V1, V2, and V3, et cetera, that are back there. And V1 detects the lowest level objects like lines or corners or stuff like that, simple features. That is fed into V2, which detects more complex features like maybe little curves or squares or areas of black, dark, and light. That feeds to the next layer that detects more complex features, and eventually you're detecting things like dogs and cats and people's faces from these simple features. I don't love the description in the book, so I'm going to jump to a different description here. This is a oh, wait. I'm very confused because just earlier today I clicked on that and it worked. I thought, I'm wondering what happened to that. Well, I think maybe it was in the exercise here. Yeah. Okay. So I'm going to jump. I thought the link was in the stuff, but it's actually in the exercise. So we're going to talk about this in the exercise here. So in the exercise, then we're going to look at this is a Python code from our machine learning class here. Where we talk about convolutional neural networks here. We haven't looked, this is what it's called Colab, and it's an environment, where you can write Python code along with text here. And so there's two types of cells. Text cells would have a description, and code cells, they're kind of a gray. When you click on them, there's a little run button you can do, and you can say run that cell for this. And so convolutional neural networks also work with something we call filters here. But these are more like vision filters. What we do is we're going to take a 4 or like a 3x3 grid and place it over an image here. So you can see this orange 3x3 grid. We're going to place it over different parts of our image and then shift it left and right. Every time we put it in some location here, we're going to do some calculations there. I'm going to do a quick screen capture here. Oops. Yeah. Of this stuff. So the green image is our bigger image here, and this is a black and white image. Black is 0 and white is 1 here. Usually you'd be doing a grayscale or color images where you'd have values between 0 and 256. But just for illustration purposes, we're going to do zeros and ones here. And we're going to put a filter over here. And this filter is going to do be these red numbers here. So it's going to be 1, 0, 1, 0, 1, 0, 1, 0, 1. So the ones kind of make an X here. And so what we're going to do is we're going to apply, we're going to take 1 times 1 here, and we're going to get the, and that'll be, so 1 times 1 is 1, plus 1 times 0 is 0, so plus 0, plus 0 times 1 is 0. So far this is just 1. And then 1 times 0 is 0. 1 times 1 is another 1. And 1 times 0 is 0. And so, and 0 times 1 is 0. 1 times 0 is 0. And 1 times 1 is, so there are, we found 3 ones here. And so our total is 3. So we're going to put 3 in our image here. And then we're going to shift this filter over 1. I think that might be easier to see with this visualization here. Oops, let me open it up in a new window here. Okay. So again, this is a grayscale image. So you can see someone's face on the right, and you can see a pixel highlighted in red. And on the left is the actual grayscale image here. So this one is actually 25. This is 140. So low numbers, like dark numbers, will be very low, like 24, 35. Brighter numbers kind of will be like 110, 179. Really high numbers will be like 240, 255, that sort of stuff are these numbers. So that's our grayscale. And again, color images are just that way, but we have a red and a green and a blue channel. And then we're going to apply a filter here. So there are different filters we can apply for this. Let's do this one. So this filter is, again, a 3x3 filter. We're going to apply it, and I can move it to different locations on my screen for this, and I'll get a different value. If I move it to someplace that's almost all white, it's going to not do what it's going to, the result's going to be 3 or a low value there for this thing. If I move to someplace that's all black, again, it's pretty low value here, you know, under 100 certainly, often down in the 20s or 30s here. So when something's all the same colors, it doesn't detect much. But when something's different from left to right, like here, I have bright on the left and dark on the right, it's going to give me a very high number here. And it's going to give me a very low number when I see the other thing. And so that's because of this filter here. So if I'm at some location, it's calculating this, and you can see the calculation it does. So these are these filters. Convolutional neural networks are going to generate a bunch of these filters and run them for us here. So I'm not going to go over too much what this does. What this is doing is reading in a bunch of images. And what we're going to try to do initially is detect images that are digits, handwritten digits for this. Let me see if I have, this version, I don't think I have these. Let me just do a quick search here. So this is kind of like the data set we're looking at here, where we have these numbers from handwriting that are written out in different ways. And we're going to detect, we want to try to learn that this is an 8 and this is a 7 and this is a 2, things like that. So we're going to bring in those images. Each of these images is 28 pixels by 28 pixels. We're going to bring in these images here. And now we're going to build our convolutional neural network here. We define how many filters we're going to apply and the size. So it's really common to do 3x3 filters, and I can do 8 of them, and then some more 3x3 filters for this. So here's where I'm defining my filters. So I say I want 8 filters. Each filter is going to be 3x3. Then I'm going to do another 8 filters, 3x3. There's also one more layer here called max pooling. That'll take a large image, a 2x2 region, and just pick the biggest part of that and convert down to one number. It shrinks our image down in half this way. But again, this defines my filters here. And then I can train my network. How this works is that the network is shown a bunch of images. Oops, I forgot to run this code here. So the filter, the neural network is shown a bunch of images there, and then it adjusts the weights, adjusts the filters to make it better. And there's a couple algorithms for how we adjust the filters. And then as it goes, it gets better. So it gets more and more accurate as it goes through this. So it was at 97% accuracy, now it's at 98% accuracy, and it can go and learn how to detect all these images quite quickly. And so you can see here, its data, it was down here, it learns relatively quick, but learns almost 100% accuracy on this simple data set. And so again, these convolutional neural networks are what cars use for that stuff. And so that's why your book is talking about them here. Where's my book? Here. Again, there's these neural networks. They are trained. So we don't program them. We program an algorithm that needs data, and then we have to show it lots of images of how this data works for this. Have you guys taken CS principles? And in the CS principles, did you do, like, I think you have a unit on machine learning or AI, and we used to do a unit where we would do, where we like train with a camera, and we'd hold up like different objects or different things, and we'd train, say, you know, this is the pen, and we'd show it a pen different ways, and we'd say, this is a mouse, and we'd show it the mouse, and it would learn to differentiate between pen and mouse by seeing those examples of it. And that's kind of like, I mean, that's exactly what CNNs are doing, is we've got to give it lots of descriptions of things like traffic lights or bicycles and stuff like that. So where do you think Google gets a whole bunch of pictures of traffic lights that are labeled that say, this is a traffic light? there. So have you ever had to prove that you're human on the computer? And so what did it show you? Well, there's lots of them, but have you done is this a motorcycle or is this a crosswalk? So you can see, you get to know where self-driving cars are not so good right now because we're getting a lot more images. My feeling is they're not great at motorcycles. They're not great at crosswalks. What other images have you been seeing in those sorts of stuff? Those are the ones I see a lot. I think maybe I had one time where it showed me bridges and I had to identify what was a bridge. I wasn't very good at that one. Okay. So again, these convolutional neural networks are here. We actually have some that are already pre-trained and are very large. They're pre-trained on whole lots of images here. So like this is an example of one that's lots with some images. This is the Caltech 101 database. This is actually a pretty small database, but it is 30,000 images that are all labeled here. And like these are all images of dogs here. And so it's trying to learn that these are all images of a dog. And you can see how varied they are here. These are all images of ferns for that stuff. So again, it's just trying to learn these images and determine it. And so, I mean, some of these dogs have clothes on them. Some of them are with other people, and some of them are just nice by themselves there. But again, it should recognize in all of these that there's a dog in the image. And so what makes, you can probably recognize the dog in each of these images. How do you recognize that this is a dog even though it's wearing clothes? Or how do you know that this is a dog and this is a person? They both have brown hair there. What characteristics make a dog there? And you can't just say things like, "Oh, it has brown hair because here's a dog with white hair." Well, then it has floppy ears. Oh, these dogs have pointy ears. Well, have floppy ears or pointed ears there. But what if you can't see the dog's ears? Like this dog is wearing a hat there. So again, the convolutional neural network has to figure out what features it should detect and then make more complex features out of those and more complex features out of those, and then try to figure out what different combinations of features make a dog and what's don't. And that's what this training does for this. Okay, how are we doing for today? So I think we talked about the 3x3 filter. I don't think I talked much about the max pooling. I think you can look that up, but a max pooling out there, if this does. So again, max pooling is again where we're applying a 2x2 filter to an area. So like again, we'd look at this image where we have a 1, a 3, a 5, a 6, and max pooling simply picks out the max. So 1, 3, 5, 6, the max is 6. So that is a 6 here. If we move over here, 2, 4, 7, 8, the max is 8. So the 8 goes here for this. So I asked it to create a picture of it, but it was not doing very well. So this is another one, max pooling. Again, it's nice. It kind of shows the colors. This is the version I use in class, where you can see first we apply the 2x2 filter in this orange region, then we shift it over to this green region. We then shift it down and do this and shift it here. In each region, each 2x2 region, we find the maximum value. So 1, 0, 4, 6, the max is 6. Here, the max is 8. Here, the max is 3. Here, the max is 4. When we do this, our image gets half as big. So we had a 4x4 image. Now we have a 2x2 image. So again, we often apply this to a very big image like a 120 by 120 image. And we applied every 2x2 grid, and we end up with a 60 by 60 image then. Well, if you can get through the exercise today, that's all we're going to do. Thursday, we're going to work on our final project with our Raspberry Pi. So I'll bring the Raspberry Pi. If you have your Raspberry Pi, make sure you bring it on Thursday. We'll spend all day Thursday working on the Raspberry Pis and getting your final project going. We've been talking about it on paper and stuff. Now we're going to actually see if we can, how far we can get with it. Sound good? Okay, I'm going to wrap this up. I've had a long day today. I'm ready to be done. So feel free to call me over if you have any questions in the rest of the exercise here.